Welcome to this lecture series on energy management system for renewable integrated microgrids. This series introduces the fundamental concepts, architectures, and application of modern microgrids EMS. These techniques are critical for achieving stable, efficient, and resilient microgrid operations under high renewable penetration. Let's begin with the concept of microgrids. A microgrid is essentially a localized small-scale power system that integrates distributed energy resources together with different types of nodes. Unlike traditional power system, a microgrid is capable of operating in both grid-connected mode and islanded mode. To maintain stable operation under these different conditions, a microgrid relies on advanced energy management systems and local control of its distributed resources. The EMS coordinates forecasting, scheduling, optimization, and control to ensure the power system's stability, reliability, and flexibility. Now let's look at the key components. First, we have distributed DG with grid forming capacity. These units provide the necessary inertial lag support and maintain frequency during islanded operation. Next are the inverter-based resources, such as wind turbines, photovoltaic, energy storage systems, and EV chargers. These devices are highly controllable but also introduce fast dynamics and low inertia, which bring new operational challenges. Finally, microgrids supply both critical and non-critical loads. Critical loads including those data centers, hospitals, they require uninterrupted power. Non-critical loads including residential or commercial consumption that can flexibly managed by demand response strategies in the EMS. Now let's compare microgrids with traditional back power systems. Or, although both aim to supply electricity reliably, their structure and operational characteristics are fundamentally different. First, in terms of structural difference, microgrids typically operate with short distribution lines and a much higher resistance over reactive ratio. Their topology is often simplified and compact, sometimes modeled as an integrated bus. In contrast, traditional grids have longer transmission lines, no resistance over reactive ratios, and highly detailed network structures. Second, regarding sources characteristics, microgrids are increasingly dominated by inverter-based resources such as photovoltaic, wind turbine, and energy storage system. These resources provide little or no physical inertia, making the system more sensitive to disturbance. Traditional power systems, on the other hand, are dominated by synchronous machines, which naturally provide high inertia and stabilize frequency dynamics. Third, let's look at control and dynamics. Microgrids exhibit fast, power electronic driven dynamics. Small disturbance can propagate quickly, requiring fast control response. In the buck power system, the presence of synchronous machines slow down dynamics behavior, making the system inherently more stable. Finally, operational challenges. Microgrids often face voltage fluctuation, frequency instability, limited spanning reserve, and high uncertainty from renewable generation. Traditional grids benefit from large interconnection and abundant inertia, are significantly more robust against these issues. Due to their inherently low inertia, microgrids are more vulnerable than traditional power systems, making advanced EMS essential for secure and reliable operation. Now let's look at why microgrids are becoming increasingly popular around the world. First, global energy transition plays a major role. Countries worldwide are setting decarbonization targets, which require large-scale integration of clean energy. At the same time, we are seeing a rapid increase in renewable penetration, especially solar and wind power. Another key factor is the electrification of transportation, driven by the fast adoption of electric vehicles. All these trends push the power system toward more distributed and renewable rich architectures where microgrids naturally fit in. Second, reliance has become a critical concern. Extreme weather events such as storms, strong wind, and wildfires are causing more frequent and widespread power outages. Microgrids can isolate from the main grid and continue supplying power, which is essential for critical infrastructures, including hospital, data center, and emergency service. In remote or islanded regions, microgrids also serve as independent system to ensure reliable electricity access where traditional grids are difficult or impossible to deploy. The third factor is economical benefits. Microgrids enable peak shaving, reducing demand during high price periods. They also supply energy arbitrage, buying electricity when it is cheap and selling or using it when price rise. Additionally, microgrids reduce the need for expensive transition upgrades by generating and managing power locally. These economical incentives are attractive for industrial and commercial users, accelerating microgrid deployment. Finally, rapid technical advances are making microgrids more capable and cost effective. Progress in IBR control technology, especially grid forming and grid following controls, improves system stability. The cost of battery energy storage continues to decline, making storage-backed microgrids far more affordable. And with ongoing digitalization and IoT development, microgrids can now collect real-time data, communicate seamlessly, and operate under intelligent EMS platforms. The main reason for the microgrid's energy management systems has become such a timely and highly active research topic is that EMS sits at the intersection of multiple cutting-edge research frontiers. First, with the rapid progress in AI and time series learning, we can now make much more accurate prediction for node, solar generation, and wind power. Models such as LSTM transformer and probabilistic forecasting methods can be applied directly. More accurate predictions significantly enhance EMS scheduling and make operations more robust under uncertainty. Second, microgrid EMS can naturally embed model predictive control. MPC optimizes control actions based on prediction horizons and handles operational constraints very effectively. For renewable-rich microgrids, MPC helps maintain system robustness and improve coordinated operation across dispatchable energy resources. Third, modern machine learning models can be used to build data-driven compliance models for the microgrids. Reduced order or black box models can speed up MPC computation while maintaining accuracy. This creates a tight connected loop between modeling, prediction, and control. Fourth, EMS is fundamentally an optimization problem. This means many advanced optimization frameworks can be directly used, including linear programming, signal co-programming, mixed integer quadratic programming, ADMM, and distributed optimization. High-performance numerical solvers can also be explored and integrated into this research system to improve its solving efficiency and quality, such as those novel quantum-based methods. Since optimization itself is a fast-evolving field, EMS naturally benefits from these advancements. Finally, microgrid dynamics are governed by complex DAE systems. Thanks to progress in numerical computation, we can now use high-performance DAE solvers with advanced numerical integrators such as those geometric constrained methods or quantum-inspired methods. All of these significantly improve microgrid dynamic simulation, speed, and accuracy. Now let's look at the market development of microgrids. In recent years, the global microgrid markets has entered a period of rapid expansion. From the first report, The microgrid market size is projected to increase from around $35 billion in 2024 to nearly $96 billion by 2030. Similarly, Future Market Insights forecasts that the global microgrid market will reach $45 billion in 2025 and grow to $135 billion by 2035, with a long-term CAGR of around 11.7%. A third report from SkyQuest estimates a CAGR of 15.6% from 2025 to 2032, emphasizing strong economical commercial adoption and the growing need for reliant energy systems. Overall, regardless of the specific research sources, all reports show strong, sustained growth of the microgrid industry over the next decade. Microgrids are no longer just niche systems, they are becoming a mainstream component of the future power systems. Before we dive into the technical details, let me give you an overview of what this course will cover. The entire series is structured to guide you from fundamental concepts to advanced EMS design techniques in a very systematic way. First, we will start with an overview of the EMS architecture and its classification, so that you can understand how different EMS layers work together in modern microgrids. Next, we will move to power profile forecasting for both nodes and renewable energy sources. Here we will introduce time series learning techniques and discuss why accurate forecasting is essential for reliable EMS operation. Then, we will build the foundation for the rest of the course by introducing the microgrid modeling and simulation framework, including component models and DAE-based dynamic simulation. The fourth part focuses on day-ahead EMS design for grid-connected microgrids, where economic scheduling and market interactions become important. After that, we extend the EMS by incorporating grid security constraints, including voltage and current constraints to ensure secure and stable operation. The sixth part of the course introduces model predictive control-based EMS, which allow us to embed dynamic models and handle uncertainty in a systematic way. Finally, we will study EMS design for islanded microgrids, especially under high penetration of inverter-based resources. This is one of the emerging challenges in the field, and we will see how advanced EMS techniques help maintain stability and reliability. Overall, this course is designed to build a complete understanding of modern microgrid EMS, from forecasting, modeling, optimization, to advanced control. That's all.